Welcome everybody to this final session of the program. So our first speaker is Jacqueline Bloch, who is going to speak about non-linearities in a driven-dissipative SSH lattice. So Jacqueline, you can please go ahead. Yeah.
Okay, so thank you very much, Manas, and thank you very much for this invitation. It's a pity we cannot go and meet in India. Maybe it's better for the planet, but it's still a pity. Okay, so today I would like to address some recent experiments we did in our lab, working on lattices for cavity polaritons, and so starting to play with the interplay between topology, drive, and dissipation. And so I'm not going to talk about all kinds of nonlinearities. I will mainly discuss solitons in topological lattices, and I chose to discuss SSH because this is really the simplest model where to see where topology can play a role in soliton physics. Okay, so very brief introduction to topology. So we all know that now that topology is actually ubiquitous in physics, and in particular when we look at the properties of particles in periodic materials, and that they can be very interesting to engineer properties which are robust to imperfection, to disorder. And so even for application, you can dream of having some channels in which you can propagate particles or light and be completely immune to any local fluctuation. So how can we understand that? So we know that when we have a crystal and that particles can hop from one side to the other, we can get extended wave functions, so describing the global properties of the crystals, and the states of the system will form bands. And so these bands are described by energy and wave function, so corresponding eigenstates, and they are sensitive to local perturbations. So if you distort the system, you will change locally the energy, and you will also change the shape of the wave function of your eigenstates. But then there are some properties. So, and in particular, what I want to say is that if you want to look at the topology of the system, you will not see it if you look at the band structure only. You will see it only if you look at the eigenstates of your system. And actually, when looking at the eigenstates of your system, you discover that there are properties which are global properties. So they are called topological invariants. And it means that they are completely immune to any perturbation and to disorder. I mean, of course, as long as they are not too big. And so, for example, you can define a Chern number, which is a property which is global because it is calculated and integrated over the entire Brillouin zone. And what you see is that what is important are the eigenstates here. These are the eigenvectors as you describe your whole band and you describe the whole Brillouin zone. And so it can be shown mathematically that these numbers are integer, and so depending on the properties, on the value of this topological invariant, you can start to have evidence for very interesting physics. And so it has been actually realized by these very clever people that, for example, the physics of the integer quantum Hall effect, where you have a quantization of the conductance, which is, and the conductance is only related to the very fundamental constant, is really strongly linked to the existence of topological invariants, and actually they are associated to each of the Landau level. And when you scan the magnetic field and you sweep the Landau level, so you sweep the Fermi level from one Landau level to the next one, actually your Chern number is increased by 1 unit, and this is why you have this quantization, very peculiar quantization of the transport properties. So what is also very interesting, and so how can you understand the existence of these quantized conductance? This is also related to the existence of H states. So this kind of orbitals of electrons, so going across the samples. And so these H states appear when you have an interface between two materials which do not have the same topological invariant. And so this is the case at the edge of a two-dimensional electron gas, because you have the non-zero chain number in the Landau level, and then at the outside of the sample, the chain numbers are zero. And so this is one of the explanations of this robust transport and this quantization and very specific values of the conductance. It's because of the existence of these H states, which are only related, which existence is only related by topology, and which are given by this so-called bulk H correspondence. So one research field which is extremely flourishing these days is to what we call now topological photonics, actually, which is to try to use and to be inspired by these solid-state physics phenomena to engineer interesting devices for light, where the propagation of light would be governed by such topological arguments. And so we see here some very important papers where, for example, you could really mimic the integer quantum Hall effect, having light propagating through the edge between two different materials, and if you put a defect between them in the way, light will just go around the defect and continue without any backscattering. And this has been done in the microwave regime, in silicon photonics platform, and in many different systems. So also you can start to play with the dissipation, and you see that, so this has been addressed a lot during the conference, the notion of PT symmetry, and you can also build interesting topological defect playing with lattice, which has some PT symmetry. So one thing that which starts to be also very interesting is to go beyond the linear regime and really try to see how interaction or non-linearity for light in some medium can change the topological properties of the materials. And so here I put some references, and I'm sorry, of course, I could not put everything, but there starts to be a lot of experimental work so depending on the platform, so for example, in conservative systems, so like for example in systems where you have an array of waveguides, topological solitons have been discussed, have been observed, and have been discussed. So solitons which appear in the gap of a topological lattice. You start also to have some very interesting paper where you have really many-body physics emerging when you have in a cavity with topological properties. So you start to build Löffling states and to emulate the physics of the fractional quantum Hall effect with light. And then you can also think about using stimulated emission, which is some kind of nonlinear effect, to fabricate a laser which is able to be triggered on a topological edge state, and there are very interesting papers on that. And then you can also try to go into quantum optics and so generate propagate quantum light in topological edge states, or trigger parametric processes in a topological medium. So what I would like to describe here is what happens when you have both topology, non-linearity, but you have also a dissipative system. So when, for example, you generate solitons in a dissipative system, can you make something? Can you use dissipation as something which is interesting as an asset to generate a new family of solitons, or is it a problem to have dissipation? And we also wanted to see if robustness properties of soliton could be somehow addressed for topological systems. So this is what I'm going to discuss. And so the outline of my talk will be the following. I'm going to first introduce very quickly the SSH model and where the topology comes from. Then I will show you how we could engineer an SSH lattice for polaritons, and I will describe to you gap solitons that we could generate in our 1D system and explain how we could so test their properties and also create polaritons that have no counterpart in conservative systems, so showing to you that we can really use dissipation as an asset. So SSH so the name comes from these three very famous scientists, and so they were interested in describing the physics of electrons in polyacetylene. And so what they fabricated is a tight binding model for this lattice, where you have so identical atoms on a chain, identical sites, but you modulate the coupling between nearest neighbor, so you have two values of the coupling. So you can write this Hamiltonian in a very simple way. You define a unit cell, and so T is the coupling within the unit cell, and T prime is the coupling between adjacent unit cell. So when you diagonalize your Hamiltonian, you find this band structure and the corresponding eigenstates. So you see that as soon as T is not T prime, you open a gap, and from the band structure you cannot differentiate whether T is larger than T prime or T is smaller than T prime, and actually it doesn't make sense in the bulk because you can arbitrarily define your unit cell the way you want, either with T inside the unit cell or T prime. So now if I look at the eigenstates, I describe their amplitude on the two sublattices. So this is why this is a vector with two components. And you see that there is a phase between the wave function of the A and the B sublattice. And so this is a parameter, the phase. And what you can do is define the Berry connection for this parameter and look at it across the Brillouin zone. And what you find is that actually you can define a topological invariant, which is called in 1D the Zach phase. And what you find is that if T is larger than T prime, this winding is equal to 0, whereas if T is smaller than T prime, this winding is equal to 1. And so this tells you from the bulk edge correspondence that if you consider a finite chain and you start with a unit cell which has T inside, so you start with a coupling T, it tells you that if you start with a T larger than T prime, there will not be any edge state because the winding is equal to 0, whereas if T is smaller than T prime, you expect to have an edge state, so to have a state within the gap located on the A pillar, on the A site. And so this is what I summarize here. You see, so here all the states, and there are no edge states. There are only bulk states which are delocalized over the entire structure. Here we compute just for 20 sites. Whereas here you have two states within the gap, which are located on the two ends of the structure. And so these are related to the topology. Okay, so if you look in more detail at these edge states, you can see that actually this one is only located on the A sublattice. So it has a maximum on the end site, then it has a 0 on the next one, and then another little antinode there, 0 again, and so on. So it is only located on the A sublattice. And the other one is only located on the B sublattice. And so we are going to define a pseudospin, which is somehow the weight of the states, the way it is located either on the A or on the B sublattice. So it's really the sublattice polarization of your states. And so for the A sublattice, so this edge state has a 1 pseudospin and the other one has a -1 because they are fully localized only on one sublattice. Okay, so to fabricate this kind of structure, To fabricate polaritons, I'm just going to give you a small reminder of what these polaritons are. So these are made of semiconductors, so microcavities are samples. So we have two mirrors surrounding a cavity. And so this is the dispersion of the cavity mode for photons located within the cavity. And then at the center, at the antinode of the cavity, we insert a quantum well. I'm sorry, the animation do not work, but it's not a big deal. Or at least I don't see them. Maybe you see them. At the antinode, we insert a quantum wells in which we can create excitations, which are called excitons, which are bound electron-hole pair, which live for a certain time before emitting light. And so what we do is that the cavity are exactly tuned to the cavity mode energy, so that when an exciton recombines, it emits a photon which can oscillate long enough within the cavity to be reabsorbed, re-emitted again. And at the end of the day, we end up with exciton-photon mixed states, which are called cavity polaritons, which present this peculiar dispersion. So they are interesting, these polaritons, because they are photonic, so these are made of photons oscillating within the cavity, and they have dissipation because photons can leak out of the structure, and there is drive and dissipation because if you want to reach a steady state, you need to pump the system, and you can pump it the way you want. You can address some particular states. We will see that this is very useful for what we do here. So the system is really intrinsically driven-dissipative. We can engineer lattices, engineering the photon mode. This is what we use to fabricate SSH. But at the same time, we have this excitonic component, which gives rise to a strong kern non-linearity, and this is what we are going to use here. So how do we probe the system? We look at photon escaping the cavity.
Jacqueline, sorry, I have a question.
Okay.
Where is the lattice? There's no lattice yet, right?
Now, here it's a 2D cavity. First,
Right.
I'm going to show how I detect, and then we go to the lattice, okay?
Okay.
So the planar cavity, it's just these polaritons. We look at photon escaping the cavity. If we look as a function of angle, which is as a function of in-plane wave vector, we get the dispersion. And then we can also monitor things in real space, do interferometry, do all kinds of optical measurement to fully characterize the field inside the structure. So then, how do we build a lattice? So what we are going to do is to use electron beam lithography to define little microstructure and etch them. So we remove all the material that was in the planar cavity, and we just keep at the end some little microstructure. And we will fabricate a lattice using a tight banding approach. And the building block, the elementary building block, which is the equivalent of an atom. When you fabricate a crystal, you put one atom, then another one, and you hybridize the orbitals and so on, will be this elementary building block, which is a micropillar. So if we look just at one micropillar, and we look from the top at the light emitting, coming out from the micropillar, this is what we see as a function of the position on the micropillar and the energy. And you see that there are discrete modes, so light is fully confined within this little micropillar, vertically between the mirrors, and laterally like in an optical fiber, because the index of refraction is 1 outside and 3.5 inside. And you see that we have a lowest energy mode, which has a maximum at the center of the pillar. This is what we call an S mode. And then at higher energy, we have another mode which has two lobes, which are actually out of phase. And this looks like a p orbital. It is twice degenerate, and we call it a p mode. And then at higher energy, we would have a higher energy modes. So then we can fabricate two coupled micropillars. And you see that the S mode will hybridize to form bonding and anti-bonding modes. The p mode will also hybridize. And then you can continue and fabricate, for example, a 1D lattice. And you see that you form extended states. So this one comes from the hybridization of all the S mode in each pillar. And then you have a gap, and then you have the bands for the P mode and so on. And if you look as a function of the angle, you see your band structure from your lattice. Okay, Manas, this is clear?
Yes, 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 yes. Thanks. Thanks.
Okay, so then we can build an SSH. So how do we do that? We fabricate a 1D lattice, but here we will change the distance between neighboring pillars. So you see these two are further apart, they almost do not touch, whereas this one, they really interpenetrate. So the distance is smaller here than here. So the coupling T is larger here than here. So this directly emulates an SSH chain. And so when you look at the band structure, what you see is that the band that was the S band is now split into two different bands, and there is really a topological gap here. And this is in real space what we see. And then there are the P bands and so on, but here we will just look at the S band.
Sorry, can I have a question? Can I ask a question?
Please.
Is it possible experimentally to have non-reciprocal couplings, so that the coupling to the right is different to the one going to the left?
So then you need to use non-linearities. So yes, we are currently doing these kind of things, but just geometrically, no, it's not possible because but yes, playing with non-linearity, you could imagine. We have actually a paper where we show in two coupled pillars that exciting them in a clever way, you can really have photons hopping in one direction and not in the other. You're talking about complex, so we could engineer also negative coupling. Complex potential is more tricky. Then you would need probably a magnetic field, I would say. Yes, but we can.
Maybe I can write you later because I'm interested in. Thanks.
Okay, super. Yes, with pleasure. Okay, so then what we did here is a defect. So it's a defect. Oh, I'm sorry, I skipped one slide. I don't know, but it's not a big deal. So you see that here, if you look at this chain, you can see that there is strong coupling, weak coupling, strong coupling, weak coupling, weak coupling, strong coupling, and so on. So there is a defect here because we have twice a weak coupling, okay? So it behaves like a defect. So actually, it's a defect between a chain which has a weak coupling and a chain which has a strong coupling. So you can see that if you look, for example, here, you really have a defect. On that side, you start with a weak coupling, and on that side, you start with a strong coupling. So you have a winding number equal to 0 here, and a winding number equal to 1. So you expect to see actually an interface state here. It's not between the end of the lattice and the lattice, but between two SSH which have different winding. And what you see is that actually you get a defect state inside the topological gap. And we could image this defect state, and you see that it is located only on one sublattice, and that so you have a dark pillar every two pillar, and you have this spin polarized defect. Okay, so this is like a characterization and the idea that indeed you have really a topological system. So just here an overview of a quick overview of what has been done so far in SSH with cavity polaritons. So we have been able, and then another group also, the group of Sven Hoeffling, to look at lasing. So it was possible to trigger lasing on the edge state of such a lattice. And so this was actually the first topological laser. Then spin-orbit coupling has been explored also. So there is the polarization degree of freedom, and it has been shown that you actually leave the degeneracy between the edge state because of the spin-orbit coupling. Then there is a method also which has been demonstrated where you can actually optically design your lattice, and so you can optically go from a lattice which is trivial to a lattice which has an edge state. So this is trivial, and there is the edge state here for this lattice. And we have also a paper where we have actually measured directly optically the topological invariant both in SSH and in graphene, and even in graphene there is the physics of SSH which is underlying this work, and it appeared actually yesterday in PRL, so I will not have time to describe that. This is linear physics, but you may be interested in all this work. What I want to describe today are experiments where we want to generate gap solitons. So how do we do that? We pump the system resonantly. So we shine a laser beam which is resonant with the gap of the system. We will pump the bulk. We will not be close to a defect nor close to the end. We will be just in the bulk. And we will shine so a laser which injects a coherent field of amplitude f, frequency w, and wave vector k. And so the system will obey this nonlinear Gross-Pitayevsky equation, where so you have interaction. This is the Kerr nonlinearity of the system, which is very strong. You have the potential, so this is the potential which define the on-site potential which define your SSH, and then you have some decay, some loss, which is described by this gamma, and this describes more or less the escape of photon from the system. So you see that in the so we will excite the system CW. So in the steady state regime, the drive will exactly compensate the loss so that you reach a steady state in the number of particles. And then if this psi square starts to be strong, then you will have nonlinearities. So what do we see when we do this experiment? So here what you see is the experimental profile that we measure along the chain. So this is an experiment where we will pump in the gap two close by sites. So this is what we call a dimer. So these are the states which are strongly linked. So this is a chain of dimer. I'm sorry, I go back. I would like, so this is a dimer, if this is a strong link. So we will pump a dimer. We have a chain of dimer. And what we do is we look at the profile of the intensity along the chain. So this is real space as a function of the incident power. Okay? So we rise the power and we measure the intensity along the system when we drive resonantly in the gap one dimer. So when it is pale like this, yellow, this is the linear regime. There is almost no signal because we are in a gap. But suddenly when interaction becomes strong enough, what we see is that abruptly there is a nonlinear jump in the intensity. We form a domain, a dimer, which becomes very bright, and this is called the gap solitons. And then as we further increase the power, there is another nonlinear threshold, and then we form again a nonlinear domain, but which is formed by three dimers. And there is the typical B-stability, which is expected both for the first jump and the second one. So now if we look at the profile, for example, of this at this power of 20 milliwatt, what you see is that so the system is very bright on the dimer which is pumped, and then there is oscillation of the intensity, and you see that on the left side of these solitons, the signal is only on the A sublattice, and there is 0 on the B sublattice. And this is the opposite on the other one. So if you look at the spin, the sublattice spin that I have defined before, the left tail is strongly spin polarized on the A sublattice. The right tail is spin polarized on the left sublattice. But if you look at the overall spin of the soliton, it is 0. Okay? And so the same for the three dimer, we form a domain which is a discrete soliton, a gap soliton, and the total spin is 0. And this has been already addressed in conservative system in a paper from Kifshar, that also in conservative system, if you create a soliton, you have spin polarized tails, but the overall spin is 0. And so this is the paper I was discussing. Okay, so then the question we ask is whether the fact that we have this spin polarized tail, which is specific to this topological gap soliton, to the fact that there are two sublattices, does it provide to the system some robustness? So sorry, I forgot to say that. So this spin polarized tail were discussed also first in this paper by Guillaume Malpuech. And so what they said, that showed is that actually the interaction with defect located either on the right or on the left of a defect like this, of a soliton like this, are different. So you imagine that you put a defect on one sublattice, A sublattice or A sublattice on the left or right. You find that the interaction with the soliton is very different because of this spin polarization of the tail. So we wanted to address that for our gap solitons. And so what we thought is to engineer optically a defect in the lattice. So what we do is that we excite locally one of the micropillar of the lattice, but this time not resonantly in the gap, but non-resonantly. And when we do that, we actually create excitons in one of the micropillar, and these excitons will interact with polaritons and create a blue shift. So what we did is that on a separate micropillar, which is sitting close by to the lattice, we did an experiment to calibrate, depending on the intensity of the non-resonant laser, the blue shift that we can locally induce because of this excitation. And we will use that as a defect. So then we do an experiment where, in addition to the resonant drive which excites the solitons, we have close by a small non-resonant beam which creates locally a defect. And we look at the modification of the properties of our soliton when in presence of this defect. So for example, here you see a small defect located on the B sublattice, and we look at how the properties of the system change. And what you see is that the second threshold is lower by quite a lot in presence of the defect. And if we continue and we increase the intensity of the defect, we see that the second threshold is really strongly reduced. So we modify strongly the properties of our solitons by injecting a defect on the B sublattice. If we do the same but on the A sublattice, and we use here the same power as the highest one that we looked with the B sublattice, and you see that the laser is even closer to the dimer, so it should influence it much more, you see that we get almost the same as with no defect. So these solitons, because it is located only on one sublattice, is really much more sensitive to a perturbation located on one of the sublattices than on the other. And this is fully reproduced by simulation, which are performed by a 1D effective Gross-Pitayevsky equation. So if I summarize, if I look at this second threshold, you see that it decreases a lot when I put my defect on the B sublattice and almost not when it is on the A sublattice. So then when we really wanted to fit these curves, we actually realized, I'm sorry that there is an animation which is not okay, it's not a big deal. We realized that actually this defect, this non-resonant pumping, has two effects on the polariton system. It creates a blue shift, as we had intentionally done it, and as I explained already. So it's a real part of the potential of the defect. But actually, you can also have some stimulated scattering from this excitonic cloud that we have generated and the soliton. And so actually it introduces some gain. And we could actually calibrate also the gain by making the system laze. And so we could so what you see is that if we take into account only the interaction that we have calibrated, we do not manage to fit properly the data. And if we include the gain that we have also calibrated, we fit much better the data. So it seems that actually this is something very interesting. Because of this driven-dissipative nature of the system, we can engineer defects and a potential landscape which is complex. So this is something that could be of interest also for you. So then what we wanted to do is to go beyond what can be done in conservative system, and in particular explore whether it is possible or not to engineer spin polarized gap solitons. And so what we did is now we also excite a dimer, but now we excite the dimer with two different laser beams, and one has a phase difference with respect to the other one. So we can modify the relative drive between the two pumps within the unit cell, within the dimer. And so here you see the profile that we observe for a given power as a function of the phase difference between the two drives. And what you see is that, so we calculate, so what you see is that actually here, for example, there is much more intensity on the A pillar than on the B one, and here it's the opposite. So we see some hint that we can actually create solutions which have a non-zero total spin. And this is what is summarized here on this experimental curve. And so what I want to show you, for example, here is the profile of the solution that we get here. And what you see is that there is actually a very bright soliton which is only on the B sublattice. And then you have a tail which is also only on the B sublattice. And there is nothing, no signal on the other side. And this really looks like a topological edge state. This is what you would get if you would have a chain which would be completely cut, so cut here between these two pillars. So what we get is that actually, because of this phase engineering of the pump, we have actually, by optical means, a situation which is equivalent of cutting this chain, so completely decoupling this part from this one, and we create an optical, a topological solitons, which is really exactly similar to a topological edge state. So we create a non-trivial interface, and so this is very interesting because then the Bogoliubov mode will be sensitive to that, so they will actually see a system which is non-trivial, and this is done in the bulk of the system. So you can find all the detail about this experiment in this paper. And so you see here that the spin is indeed absolutely non-zero. And what is interesting is that you can show that these solutions are not stable. So what the theoretician did in this experiment is that they create this spin polarized soliton, and then at t equals 0, they put to 0 both the drive and the dissipation. So they transform the system into a conservative one. And what you see is that these solutions are completely not stable. So there is no way you can generate and stabilize this solution in a conservative system. So we really take profit of the dissipation to create these new solutions. So to finish, I would like to summarize. I've shown you that we can create gap solitons which have this spin polarized tail. These spin polarized tails gave them some new properties, some interesting properties with respect to defect located on one sublattice or on the other. And by the way, I showed you that we can engineer non-Hermitian potential landscapes, and then that we could get actually these spin polarized gap solitons, which are new, I mean, maybe open a new playground to play with this system. And so what is next? Now we have all this playground with 2D topological insulator, and I'm sure that there are many, so there are already many proposals and many interesting things playing with non-linearity on edge states or in the bulk. And so before finishing, I would like really to thank our collaborators.
Sure.
Sorry?
Okay.
So I would like to thank my group. And so here it was just after the lockdown, so we were super happy to go for one day to the seaside to have some fresh air. So I would like to thank particularly Nicolas Pernet, whose work, I mean, he did all this work during his PhD. I would like to thank our collaborator from Lille in the group of Alberto Amo, and our theoreticians friend Guillaume Malpech and Dimitri Solnishkov, who helped us a lot with the simulation, and particularly also the people who grow the samples in our lab and who fabricate these fantastic lattices. And with this, I would like to thank you very much for your attention.
Thank you, Jacqueline. So now we are open for questions. You can please unmute yourself and ask questions, or you can even type it in the chat window.
Okay, so I have one. In fact, Jacqueline, so thank you for your very nice talk. It's more about like to understand really how it works, because the driving, I understood that you pump, you send this F e to the minus I omega t, and this is your drive. But dissipation, sorry, I did not understand really how it happens in your system, sorry.
Oh, okay. So it's just the fact that we are within a cavity.
Yes.
So it has two mirrors, and the reflectivity is not one. So somehow this is the lifetime of photons within the cavity.
Okay. So this is there, and then you pump with your additional drive to okay. So, but then at the end, when you showed that you cannot stabilize the gap solitons if you do not have driving nor dissipation. So how do you cut dissipation if that's inherent to your cavity?
No, but this is not an experiment, and this is a calculation.
Okay.
This is a simulation.
Okay. Thank you. I understand better. Thank you.
Simulation, yes.
Yeah, actually, Jacqueline, I had a doubt about this plot. The thing is, so with drive and dissipation, this is a stable solution, is what you're saying, right?
Yes.
In the sense, is this like, so that means these are exact soliton solutions for the driven dissipative problem? I mean,
yes.
I see. So in the sense, they actually have analytical forms for this, for the soliton solutions.
Yes.
The driven dissipative case. I see. And there's no experiment yet on this, is it?
About what?
Yeah. So is there an experiment for this simulation?
No, but there is no way you can do that, because usually your system is either, I don't know if you can imagine that to be able to close the dissipation, but usually what we want to say is that, for example, there is a very nice review paper of Kifshar, who is describing topological physics in nonlinear medium. So he's explaining and actually demonstrating that these solutions, that gap solitons in SSH in conservative system, they have a spin equal to 0. And there are no solutions, you cannot imagine a steady state solution which have non-zero spin. So this is, and we check that indeed if you start with your solution, if you impose your solution in a conservative system, you just kill it. It's not stable.
I see. Okay. I see.
So,
Thanks.
may I ask a question, Manas?
Yes, of course.
Sure, go ahead.
So in one of the plots, you were talking about changing the strength of the non-linearity. I was wondering if is this how does this tuning happen? How can you tune?
No, I'm not changing this. Sorry, I was maybe not clear. I'm not changing the strength of the nonlinearity. I'm changing the strength of psi square. I'm increasing the drive. So I'm increasing the field that I inject, and this term starts to be important.
Right. So effectively, you can just change that in some sense, like the number of particles is what this size.
Exactly.
Okay. Very nice. Okay, thanks.
Okay. Any other questions?
Hello. Hi, I had a question.
Sure.
May I ask? Yeah. So how do you increase the incident power? Because I see that the omega here, it's a single frequency. So do you increase the number of photons, or do you increase the frequency of photons?
I increase F.
Okay. So it's the amplitude.
Amplitude of the field, yes. The frequency fixed. The frequency is this one, and I just shine more and more intensity on my
number of photons you're increasing.
Yes.
Okay.
Yes. Any other questions?
Hello.
Yes.
So yeah, if I understood clearly, so this is this SSH model driven by some external field.
Yes.
Right. So recently there is a paper by RRI group. I forgot the name. Vivek Vyas is one of the authors. So where they studied the same model, SSH model driven by external field, and they showed there we can have three phases. One is this trivial insulating phase. One is this non-trivial topological insulator phase, and there is something called this metallic insulator. I think
Yes, so this is what I showed. This is this one.
Yeah. So like with
You
the
can either have a gap, close the gap, and open the gap. I think that's what you're talking about.
no, no, that is fine. So with the application of this external field and the parameter of that external field, we can have this some kind of Mobius strip metallic phase where we see one winding in the band structure.
In the metallic phase,
Yes.
I would be. I'm sorry, I don't know this paper. Maybe you could send it to me.
Yeah, yeah, definitely, definitely. So
Okay,
I'll yeah.
okay. I
So
would be
it's
interested to have
recent paper. It's like last month.
it.
Yeah,
Okay, okay. I
yeah.
missed it. Okay.
Oh, yeah. Thanks.
Okay, so I guess we are running out of time. So thank you, Jacqueline, for the very nice talk.